Welcome to Westech Direct's discussion of wax and investment casting. Foundry owners, casting engineers, even foundry buyers often have lots of questions about wax. What's the shrink rate? Tell me about the surface finish and cracking and pressure and types of wax. And I'm hoping we're going to cover all of that today. I want to introduce two seasoned casting wax veterans, Erik Dahlin and Erik Niay. Erik is vice president at Westech. He is extremely versed in wax and on the technical details. He's innovative, spending time in the lab developing new formulas and has decades of investment casting wax experience. Aaron also brings a scientific perspective to sales with an engineering degree, and he learned investment casting hands-on working in the PCC management program, but he's also looking at this from a Foundry's business perspective. Gentlemen, welcome.
Thanks for having us.
So today I want to talk about precision investment casting, particularly the wax aspect of it. And I'm not talking about jewelry, but really about foundries, the aerospace and commercial casting and automotive and medical. And if our audience here is foundry owners and precision investment casting engineers and foundry management and buyers, I want to know, what should they really be thinking about when they're choosing a wax? Like, what are some of the broad criteria that they have to think about?
You know, each project tends to come to be a little bit unique. However, there are a lot of things that are found to be in common. And typically, the number one question people ask is about the wax shrink. You know, how big is my wax going to be when I inject it into the tool? What's the resulting part going to be? That tends to be the first and foremost type of thing that an engineer wants to make sure that if they're looking at a wax, it's going to be the same shrink so that the resulting casting is the same size.
Shrink rate. So if we just listed them real fast, Erik, if you were to list 7 things,
It would be shrink. It would roughly in this order. It would be a shrink rate. We would want to go for surface finish. The next big thing is dwell times. We'd like to shorten the actual casting cycle and the injection cycle. So dwell time is an important one. And then we go right next to injection pressure. That's the next big issue. And then we're down to part configuration. That's very important. Some parts are a lot bigger. There's holes in a part, i.e. that, you have a large aluminum piece that you need to drag out of the die. That affects what type of wax and what kind of fillers we'd like to use from there. And then right into shell crack. That's the number one thing. How does it handle the wax through the process all the way to shell cracking? If I had to jump, the two main things would be shrink rate, obviously, like Aaron said, and then right to shell crack. How does it perform in my foundry? That's the quick answer.
So let's talk about shrink rate since it's so important. So I want to look at it from two perspectives. Aaron, let's start with you real fast on shrink rate. What are the business problems? What are the foundry problems? Like, why are they coming to you and talking about shrink rate? And what do you see happening on the business side of things? And then Erik, we'll come back to you and talk about some of the technical aspect of it.
Sure. So shrink rate is so important because there's multiple processes in precision investment casting that are going to make the part smaller. And it starts with how you cut the tool. The wax is going to shrink. The shell is going to shrink a little bit. The metal is going to shrink. So we kind of have 3 different processes, and we're trying to get to this final dimension. In some cases, as little as within 5 thousandths of an inch. Some other tolerances aren't quite as tight, but we usually have to be very precise, and the precision investment casting process kind of allows us to do that. What people are really ultimately wanting to know when it comes to shrink rate is what my final part's going to look like. And our process is to try to simplify that into kind of one linear dimension. So we use a very simplified disc tool, and we make injections at specific parameters, and we can then understand what the kind of inherent shrink value of that wax is. However, in process or in the foundry itself in the wax rooms, we can change that a little bit based on the parameters of those machines, whether it's a different temperature, pressure, injection cycle. We can actually alter how much wax is going to shrink to get closer to the end goal of whatever that particular part needs to be.
So Erik, you've literally been in the lab developing waxes. What are some of the things that actually affect the shrink rate in a wax, and how does someone know which wax to buy?
Jason, that's a great question, but I might have to find your place and end the conversation because a lot of that is proprietary, but there's a lot to go into it. But let me give the 10,000 foot answer. Wax, when we say wax, a layman's person like yourself, you think of a candle wax. And right out of the gate, they say, oh, well, it's just wax. Well, there's probably averaging between 6 to 12 items that ingredient wise that we put in the wax. When people think of wax, they think very generically, but it is a step removed from being almost a thermoplastic because the temperatures are much higher. For instance, if you were to put a candle wick in our regular powder wax, it would burn out the candle. It would not burn in the normal configuration. So with our ingredients, improvements in what we're able to accomplish. We're maintaining dimensional stability. That's the number one issue from batch to batch to batch. That's a big issue. That goes back to the actual formula and our raw materials, maintaining our raw materials on a regular basis, meaning we have to qualify our raw materials as they come in. We're very specific about that to maintain our batch to batch consistency. And then, like Aaron said, when we go through and do the dimensions, we measure our dimensions, but we have three main categories. We have an average one, which is 65% shrink rate. Then there's the 80 to 85% shrink rate. And then there's the 55 shrink rate. And in that order is about the popularity they're used, 55 being the largest, 65 being the middle, and 80 being the smallest of those. But we try to keep it within those categories because people get off the reservation a little bit when they start asking for some odd, but those are 99% of the sizes that we deal with.
Do either of you guys have a tip for a casting engineer on wax shrinkage?
I think your best bet is to find a tool or a part that you can run consistently at each press on your wax room. Pick a round of settings that is similar to maybe what your product profile is and test that part weekly, maybe bi-weekly, and you will get eventually a large sample of data that's going to say this is the exact same part, the exact same parameters, albeit maybe different machines, but you'll understand how those dimensions change maybe from machine to machine, which they certainly can, also possibly seasonally and also possibly from lot to lot. So what I would suggest is real-time data from an actual part or a representative type of part. And that's kind of why we fall back to this disk tool, because it's the same part, the same parameters, very simple to measure. And we've got years and years of data to kind of give us an idea what category a particular wax is once we get that information.
And I assume if they need help on that, they can call you?
Absolutely, of course, anytime.
And also to add into what Aaron's speaking of, one of the things that we do also is we try to ask our customer for a die that they use consistently, that they have a lot of history with, that they have dimensionals with, and sometimes in some cases dies they're struggling with. Just send us the die. We have liquid and paste machines here that we do. And when they send it in a lot of cases, they're busy. They can't focus on that. It's what we do. So we focus on it for them and we can help them with dimensions and the way the part's injected, with dwell times, with pressures, all kinds of extra.
Oh, that's amazing. Because you have your own lab.
Yes.
Yeah, amazing.
We have our own injection facility here. Yes.
Tell me about surface finish quickly. I mean, I think most of the investment casting guys out there know why it matters, but are there any tips or tricks? Like, when I'm choosing waxes, how do I know that the surface finish is what I expect it to be, that it's going to be consistent? Like what do I need to know there?
The biggest issue is when we get down, the newest trend in the last 10 years has been paste wax. And you get an item called flow lines, and you also get an orange peel effect. And if you get too low in temperature, that's where the criteria, and a lot of people want to move to a lower temperature in the injection process. So you have to watch that. So I like to go down to the point where that's happening and then back off the temperature a little bit, and depending on the wax. And it's also depending on what kind of surface, meaning some of the waxes, filled waxes, have a rougher finish. Non-filled waxes have more of a shinier finish and not as, we call them pock marks, but there's marks on there that some people don't like. And there's a lot of misconceptions about what a flow line is, what a flow line isn't. And it comes down to what's going to go on to the casting, the actual metal part. And we can help people with that on a regular basis, because there's a lot of times that parts get rejected and they shouldn't be rejected. It's just an oddity in the part. We call them a resin line, but it's where colors come together. Sometimes you have a little bit of hot wax, cold wax, they rub together and it looks like a flow line, but it technically is not. And that will not make its way to the casting, the metal casting itself. And Aaron and the guys out in the sales department, they deal with that a lot, and they have to go. And that's where the visits, when they actually visit the customer, that's where the rubber meets the road with the sales guys.
Where the wax meets the casting.
Yeah, there you go.
So we have always worked on a philosophy that we say cold wax, warm die. And our philosophy is that we want to cool wax from the inside out, not necessarily from the outside in. Some people do like to run tools or the platens, I guess, on the presses really, really cold. And that does form a shell on the outside. But in some cases, it doesn't necessarily always cure the part as fast as having a little bit colder wax. Now, Erik is definitely right. The cooler you go on temperature, the more susceptible to flow lines, or generally the higher the viscosity of the wax is. So if you can keep it a little bit warmer, as well as keeping your tool kind of in that ambient or room temperature range, you're going to end up with very nice, smooth surface finish in pretty much kind of anything you get from Westech, or particularly non-filled waxes are going to look even shinier on the surface.
So let's talk for a second about dwell times. Erik, what does a casting engineer need to know about dwell times?
The cold wax warm die, and with the dwell times, in a lot of cases, they will find that people think that they can run the platens a lot colder. Now, the platen's function is only to maintain a consistent mold temperature throughout injections, because keep in mind, you're injecting hot wax into an aluminum die, and it's going to take on that heat. So the platens are just to maintain an even temperature. People turn them way down thinking they're cooling the wax, but what they're not doing, what they're doing and what they don't understand is the wax inside is very, very hot. It's that whatever temperature, and it insulates itself. So what we try to do is walk them through that part of it. And then we try to, and get in the dwell time. So let's say they're 12 dwell times, a minute 30. We start to back that off at 5-second intervals, and we try to maximize, because the faster they can get the part out of the mold, the more productive they can be. 30 seconds here, a minute here is very valuable to a foundry that's running 1,000 parts a day. So that can be very, very valuable in that case. But you have to work through the wax depending on which wax they're using and the size of their parts. So a part that has a pull or is not very big is obviously going to be very fast, but then you've got a part that's the size of a shoebox. Well, that's a whole different ballgame, and you got to deal with it accordingly. But you can usually, in most cases, when we go to a foundry, we can shave between 20 to 15 to 20 seconds off just from their ability and the way they're handling their wax.
Interesting. Aaron, any quick tips on dwell time?
Yeah, I would break the dwell time or cycle time. And there's kind of a couple maybe clear definitions we want to make here, but it kind of breaks down into 3 parts. You really only have 2 settings on the machine. One is called cycle time, which is going to be the pressurized injection time using the hydraulics from the system. You're also going to have hold time, which is no hydraulic pressure. It's just the machine holding the tool in place. But even before all that gets started, you have, I would call, injection time. So to start, the tool is empty, of course, it's just filled with air. And the number one goal is to completely replace that air with the wax. So you do have a time where the wax needs to fill the cavity, but then you also have packing pressure time plus the hold time. So I really kind of break it down into 3 things, and kind of like Erik said, depending on what the part looks like or how big it is, you'll need to address for how long does it take to fill, how much time do we want to pack the pressure, and then possibly how much time do you want to continue to hold the part without pressure. Typically, you don't need to hold it too much after injection. However, with more complicated tools, automated slides and things like that, that does sometimes come into account, because we don't want a slide to pull a pattern apart while we're trying to remove it from the tool. So we'll hold it in there a little bit longer to kind of cool the outer portion of the wax a little bit longer.
So how do they optimize those dwell times, or how do they figure out? I mean, I imagine it's complex, but how can they optimize one aspect of that dwell time line?
The cold wax warm die.
Mm.
It's very simple. That usually decreases dwell time just by using that theory and that concept right out of the gate.
Cool. And then another thing you just mentioned, Aaron, was pressure. So how does injection pressure affect everything that we've been talking about here? And what's a tip for our casting engineers out there?
Sure. For our industry, somewhere between probably 100, maybe as high as 600 PSI is kind of the operating range. I usually don't go above 600, although some of the presses I think can get up to 1,000. And really what the pressure does, first and foremost, is it helps control the flow rate of the wax into the tool. So if you have a really low pressure, you can only bring the wax into the tool at a very specific rate. If you have a higher pressure, you can bring it in a lot faster. In optimization, part of the goal is to fill the tool as fast as possible while still getting good surface finish. And then we can use that pressure to cure the wax a little bit easier, a little bit faster. And the higher pressure that you apply in that process, the faster you're going to build kind of that shell around the wax so that you can pull it out of the machine or out of the tool in one piece without it falling apart. And that's really the main goal. Is it's got to be in there long enough to have enough, I guess, sturdiness to be removed from the tool. It's not going to fall into break apart, or it's also not going to be too soft where it's going to misshapen or maybe deflect and move a little bit after removal from the tool. So you can use pressure to kind of speed it up as well as cure it while we're in that pressurized cycle time.
Jason, I have a very, very layman's term and give you the very 10,000 foot engineer definition. If you remember back when we were kids and you did paper mache and they took the balloon and you wrap the paper mache around the balloon and they would get hard and you pop the balloon and you have a nice head to, decorate. That's kind of the concept is when you're filling it up with pressure, you want to push up against the walls of the die like a paper mache, get it start to solidify, and then you can let the pressure off.
As someone who develops wax, what are some of the criteria that affect that? I assume there's like viscosity and melt point. And then if I'm an engineer out there, how do I have any clue which wax to pick? Like if you took a couple waxes from Westech and you compared them, how would they be different in terms of dwell times and injection pressures and melt point? And like, what are the differences between these waxes? How does someone even know where to start?
It goes back to the first question of the day. You really need to understand what the goals are of that particular engineer, assuming that they're looking for something different or possibly looking for something the same. So we need to understand what the goals are first and foremost. Viscosity is a big part and something that we haven't talked a lot about yet today. And when someone is trying to understand their wax versus somebody else's, we've talked about the shrink rate. Drop melt point is going to play a role in how fast it's going to melt, not only in the machine, but also how fast it's going to melt in the dewax operation, whether it's autoclave or fire type of stuff. So that's important. The viscosity is going to tell us more at what temperatures is this material going to inject in kind of a liquid form or more of that kind of paste form. So we need to understand what their current injection temperatures are, maybe what their current viscosity is. And so if the goal is to have something that's very, very similar or what we call drop-in replacement type of attitude, we're going to really need to understand what that viscosity is in comparison to what they're currently using so that we can apply that to basically imitate the flow at the same temperature, same pressure, and essentially aim for that same viscosity.
So if I were going to summarize that real quickly, if someone comes to you, one of your first questions is, are you replacing a certain wax or do you have a problem that we need to fix? And if they're coming to replace it, then you're going to look at certain key factors, melt point, viscosity, what else? Like 3 or 4, what are 3 or 4 key factors that you're going to look at to match?
I would say certainly first and foremost that dimension, that shrink. We also talked about what we call sink or cavitation, which is going to kind of give you an idea on how flat or not flat a wax might be after it comes out of the tool. Viscosity is going to be important. Melt point is going to be important.
One of the final things that we're leaving out is cost. There's products that are less expensive and more expensive. And in some cases, you don't need a Cadillac where a Chevy will be just fine. And there's some cases you need a Cadillac and you're doing very intricate parts, aerospace type one-off parts that is very important. So cost is a large factor anchor in that.
And availability, right? I hear there have been supply chain issues as well.
There is that too.
So I don't know if this is relevant for this discussion as much because we're going to have a whole different discussion on shell, but you guys mentioned earlier on about shell cracking. How does wax factor into shell cracking?
Well, that's the age-old question. Is it the shell or is it the wax kind of trail that we go after? The difficulty with trying to understand that is wax is always going to expand as you heat it until it starts to actually melt, and then you're relieving the pressure. So the goal here is to make it through the dewax process with a strong enough shell or a wax that doesn't expand too much to be able to put too much hydraulic force and crack that shell open. So how does it play an effect in there? It's really kind of a combination of the two, but really what we shoot after is we want lower melting waxes that are going to take less time to go from solid to liquid, and they're going to relieve the pressure in that mold, whether it's in the gating area or the pattern area, sooner than a higher melting type of wax.
Interesting. Erik, any tips on your side?
Aaron touched on it very well, but one of the things, again, to bring it down to more of a basic terminology or into our movement here is you have the wax, you want a delta T change between 10 degrees between your gate wax to your pattern wax. That's a very basic in the ICI problem. But then you have the shell room, and the shell room is a whole different animal in itself. Some places have really good shells. What do I mean by that? Their MOR bars are running around 500 PSI. That's a great number. And some are running lower. There's atmospheric problems. There's a lot of other issues that happen in the shell. So it's a dance between the wax and the shell. And at Westech, we're really making a real move in that direction to be able to control the wax and control the shell at the same time, and have a package deal to make everything much easier for the engineer / foundry and whatever they're doing.
Very cool. Tell me about dewaxing.
There's two different types. There's the autoclave, and then there's a flash fire. Those are the two different types. The autoclave is a pressure. Essentially, it looks like a vessel. If you've ever been a diver, where they go in and if you've got the bends, you got to go into a capsule with pressure, and it's pressurized, and its steam comes up in a very fast rate. It's very rapid. Then you have the flash fire, which is just like it sounds. It's a oven, and it's literally flames underneath it, and you're melting out the wax like it's a bonfire underneath it, and that's an enclosed system. They both have their features and benefits, but I don't think there's a better one to use or another one. In a lot of cases, the foundries have what they have, or they bought, what they've been using for years. I've been using an autoclave for years, or I've been using a flash fire for years. And some waxes can be affected by it, but in most cases, they run about the same, give or take. That's the dewax. And again, you're removing the wax from the mold, and then they burn the molds, and then they have to pour in the metal at that point, providing the mold and the wax is clean.
Cool. Aaron, anything to add to that?
I would say that's traditionally a lot more people start with autoclave. That's a little bit of an older process. It doesn't remove all of the wax, but it does remove a good portion of that material. Some of the difficulties in both processes are kind of the orientation of the mold, because typically we have a pour cup on the top. We turn the molds over, and if there's an area in that assembly that isn't able to drain the wax by gravity, you can get wax kind of caught up in some of those areas. And therefore, it certainly requires much more of kind of the post-firing process to burn the rest of that wax out of the mold. In the flash fire process, we're starting at a much higher temperature, typically oxygen-rich environment, and we're going to get rid of a lot more material in that first initial cycle than we are going to be with the autoclave. There's also no pressure involved. So in the autoclave process, you require a couple other pieces of equipment that can be expensive, dangerous, hard to maintain, because you need to get up to, in some cases, 90, at least 80 PSI in a very short period of time in a pretty large volume kind of situation. So it requires a good amount of energy to get that all pumped in and heated in order to stabilize the system inside. The slower that you pressurize that system, the more unbalanced it is, and you tend to have more issues with the shells cracking because you can't balance those forces.
Interesting. This is a very complex process here.
It is.
I know I need to get you guys out of here at some point soon. If you had some quick tips, I know there's a lot of different kind of waxes. You have soluble and pattern waxes and gating and stick wax. Are there any tips for the engineers out there around these different types of waxes, or anything that they should know? What can you tell them about those different types of waxes?
If I'm going to offer up a new engineer, is every foundry that I've been into and or successful foundries, they are always using a reclaim wax with a virgin critical part, i.e. the golf club, if you're making a golf club, and then make that virgin, and then make it the gate wax and use that as a reclaim. There's a lot of cases people try to trip over $1 to save a nickel, and they want to say, look, I'm using a blend wax. But the problem with the blended wax or any kind of shortcuts on the critical parts is you get ash, you get dimensional instability, and sometimes you get shell cracking just because the wax is odd. So you're better off staying with that, and that keeps it a very, very level playing field and doesn't change it, and you can count on the product being more consistent, obviously a virgin product with the reclaim, and you can maintain that. So right out of the gate, for an engineer that's just kind of cutting his teeth, is sticking that. And also try to keep it as simple as possible. Try not to overthink things too bad. Wax flows like water. If you've got a dewax and you've got to have it flowing out of the shell, think in terms of water flowing out of a shell. And that would help out a lot, but try to keep it as simple as possible.
Aaron, anything to add there?
Yeah, I would we tend to push the philosophy that filler, which is one thing I haven't really spoken too much about today, which is an additive that we can put into pattern wax. It essentially is not wax at all. It's a solid material, but we really view filler as kind of a crutch in the wax room, right? Essentially, it's going to make your material more expensive, no matter what kind it is. In two cases, the actual material is more expensive. One case, it's cheaper, but it also makes your product a lot heavier. So you need to buy more in order to make the same amount of parts. So It never makes any budgetary sense in that case, but all you need to do is spend a little bit more time understanding the presses and kind of going back to having a tool that you can shoot on a weekly, bi-weekly basis, understand how one press or different parameters kind of differ. If you're maintaining your presses and you're maintaining your wax process, there's really not a big reason you need filler, except for try to get to maybe a little bit of a larger size or AKA less shrink. In our case, our new GelSet product lines are designed to basically use no filler and still be able to match these mid to really low shrinking type of wax rates. So we don't really see that there's a need for them. They just make more expensive, and it's something else you got to clear out of the shell once you've de-waxed your molds or your assemblies.
Cool. And so there's something exciting in there that I've been reading about. So you guys talked about cavitation, and then you just dropped a little bit of a mention of this GelSet 2.0. And it sounds really interesting. And so, Erik, what can you tell me about the development of GelSet 2.0? Like, why is that a new kind of revolutionary, amazing wax?
So about 5 years ago, we developed the GelSet product, and we were very excited about, and it had good dimensions. Like Aaron was discussing earlier, we were able to use less filler and get to the point where we were cutting filler in half. In the last year and a half, we've developed GelSet 2.0, which we've taken cavitation, reduced it to a whole new level. To put that in perspective, normal waxes cavitate at a the linear dimension ones, the middle ones at 6.5%. Usually cavitate around 30 to 35 thousandths. With the new GelSet 2.0, we're at 20 and 25. It's significant that we were able to reduce the cavitation that much. It's unprecedented. What does that do? Well, what's exciting is both when you're making your injections through any kind of temperature variations, the cavitation stays the same. Essentially, we've taken cavitation off the table. Now you only have to worry about your linear dimensions, and that's it. And we're very excited. We've been able to do this with no fillers. We're able to match dimensions on parts that normally needed 40% filler. We don't need to have any filler at all. In fact, we're only using filler as more of a cosmetic situation, which goes back to flow lines and things, and it's a much more complicated conversation. But it's very exciting, and we're getting ready to. We're slowly putting our feet out of there, but we're getting ready to launch it in Q1, Q2 here, and we're really starting to make a big push on it.
And I would add that the original GelSet line, with maybe exception of one product, we typically needed to be a little bit of a higher temperature. 135, 140, 145 was definitely a good temperature. This new line of GelSet waxes can all pretty much operate at 130, possibly even sometimes a little bit lower for that generation of machines and processes that want to use kind of the quote paste or higher viscosity injection ranges. So we've been able to apply that to I guess kind of, what do I want to say, be more applicable to a larger percentage of the foundries out there.
So tell me, what are some ideal products or areas in which someone would use GelSet 2.0?
And exactly all of them. It is better. I'm sorry, it's better than all the waxes out there. This cavitation is on such a, I'm sorry, I might have to edit that out, but it's on such a higher level than we currently have. We haven't made an official launch of it of any kind, but we're excited about that.
And I would say, at this point in time, before we've even launched the GelSet 2.0, the GelSet 1.0 has been very successful. We're not quite at half, but almost half of our customers are using some type of GelSet pattern wax. And so we've got a wide range from really higher end aerospace foundries all the way down to people that are making doorknobs and hinges and things like that for homes, and kind of anywhere in between. So we're able to fill really thin, complex parts, but also fill the really big, kind of thick, larger construction or commercialized kind of parts, we call it.
And so GelSet 2.0, tell me about cost. You say all these amazing, great things, and then now I'm sitting here worrying that it's going to, cost more than my foundry can afford.
Well, it doesn't have filler in it.
So it's more effective.
Agreed. And like I said before, anytime you add filler to your product, you are adding costs. It's either direct literal cost or it's density, which is going to cost you shipping or just overall more money for you to make the same amount of parts, more wax to make the same amount of parts. So we are able to keep these things, gosh, I'd venture to say probably one of our cheapest virgin waxes is now the new GelSet 2.0. So it certainly is cheaper than filled waxes that we have in our arsenal. But even right now, we're pricing it even lower than some of our GelSet 1.0 products. So it's very affordable. We certainly encourage people to use it as a virgin type of material versus trying to blend it. We can save money on the gate wax by recycling all of that stuff. And for those who are a little bit more concerned about sustainability, that's a great system because we're recycling a good portion of that autoclave or flash fire material to return back to the foundry as that gate wax, which is not nearly as critical as the part or pattern wax that we're using. That's right.
So, crazy question for you. I know it hasn't officially launched, but if there are people out there looking to test or to figure out if it might work for them, are there test batches available? Is that something they could call you and kind of get the sneak peek of?
Absolutely.
All right, you guys. So this was a deep dive into wax for investment casting, but I see that we still even just touched the iceberg of how much that someone needs to know. And it sounds like you guys have a ton of experience. If they need something, it sounds like they can just reach out and get some advice. You guys are even willing to test, with them or in your own lab and work things out. Does that sound about right?
Perfect.
That's right. Trying to make investment casting easier.
All right. In our next conversation, we're going to talk with the team at Westech Direct about shell products. So make sure you follow us so that you get that and more. And of course, if I mentioned, if you have wax questions and you want to talk with the team, just give them a call at 951-279-49. Or you could visit westechdirect.com, just like it sounds, Westech. You can see it on their badge there, westechdirect.com. Until next time, keep casting.